I'm going to talk about some questions that actually came from both economics and I would say computational linguistics that lead to mathematical questions in collective intelligence. And I'll tell you a little bit about these questions, and I'll tell you a little bit about what we know about them. Now, I realize that this is quite a diverse group of people here. So please feel free to interrupt me at any point to ask questions. I wasn't planning to do any proofs, but I think even the models, even the language, the mathematical language that I'm going to use, I mean, feel free to slow me down at any point. And part of the incentive for that was actually some recent work that we are trying to finish up, but the postdoc who I was working with left to industry, so I was hoping to finish it by the talk, but this didn't happen. So, okay, so let me start with the story. So there's a huge, if many of you in the audience know that there's a huge body of work on mathematical work on learning on networks. I can do nothing but recommend, the first thing that I can do is recommend one mathematical survey of this area is a paper we wrote with Omer Tammuz. It's called Opinion Exchange Dynamics. And there are many, many models. What I want to talk about today, just given what I believe is the background of some of the people who are in the workshop, is talk about two Bayesian models. So we're going to talk about models where the agent, the people, the parts of the intelligence systems are Bayesian, the applied Bayes rule when they compute probabilities. And I'm going to talk about the newer and an older family of models. So the older family of models are these models from economics or from game theory. So these are older. They go back to the 1970s or even before. And then I'm going to talk about the models that I learned about from the community of computational linguistics. And these are much newer. These are around the first reference that I found is around 2010. And even though the models are different, there's some mathematical commonalities, and I want to tell you a little bit about this. And for me, I mean, maybe for you this is not an attraction, but for me, one of the attractions of these models is that each part of the system or each person or player in this model is somebody who's computing, applying Bayes rules. So they compute probabilities and conditional probabilities. They compute expectation, they compute conditional expectation. So I must say I relate very intimately with the various parts of the system here, and it's really nice to try to understand the system as a whole. Questions, anyone? Okay, so let me start from the econ models. These are the older models, and these are mathematical models. That, there are many families, but for concreteness, I'm just going to talk about these families of models that I describe over here. So I'll try to draw some picture. So it's collective intelligence. So individual intelligence is going to be in the nodes, right? So there's going to be a graph. Maybe this is my graph, and it's a directed graph. And the nodes are the people, they have the individual intelligence, and the edges say who observes whom, right? So maybe in this example, there are three people, and this person over here observed this person also observed this person observed this person, right? So there's the individual intelligence is what is in our brain, but some people observe what other people say or do. So that's the basic underlying parameterization of the model in terms of who observe what. And what are they interested in? Sorry, maybe I'll go a few slides at the time so you can see the picture. So what are they interested in? They're interested only in one thing in this model. They're interested in to know what is S. S is the state of the world, right? So, I don't know what it is. Is the stock market going to collapse or continue go up forever? Is civilization going to end in the next 100 years? It's something that, something that we're trying to estimate. It's not something that we have an impact on. You're just trying to estimate it. And the mathematical assumption that we are going to make it, so maybe just for an example to make, so e.g., S can be plus or minus. So maybe plus means that the stock market will go up for another year. Minus means it will crash this year. And then what people get in this picture of the network. So here are three people. I forgot already who observes whom. So maybe this was the picture of who observe whom. What people get is they get signals coming from a distribution. So this gets a number, so this gets some number 0.82, this gets maybe minus 0.57, this gets 0.32, but where are these numbers coming from? They're coming from a distribution that depends on the state of the world. So maybe in this example, we have a distribution F plus that, maybe the density looks like this, and maybe F minus, the density looks like this, right? So you cannot say for sure, just sampling from one distribution or another, what's the state of the world. But, if you get a number over here, say, well, it's very likely coming from the second distribution. If you get a number over here, say it's very likely coming from the first distribution, you can try to work with that in order to do what you do. So what's the game here? The game here is that there's individual intelligence. The individual intelligence is given by these numbers here. So that's the numbers that we just talked about, these numbers here. These are the individual intelligence, but now they watch each other. And now I'm going to describe one model, again, one model coming from economics that says how they interact, and then another model coming from linguistics on how they interact from this point on. So maybe I'll go a few slides so it won't be. So here's the mathematical formalism, and please, again, stop me or ask me to slow down if you want, right? So what does each individual have? Each individual has a memory or a history. And the memory and the history of that individual is what is denoted by HV, and there's a time index. In this time, it's 0. And at time 0, I use the probability notation of sigma algebra. At time 0, I only see the number that I got at the beginning. So this is my history or memory. What we have here is history / memory. And then what do? I step number 0. V is a node in the graph, right? V is one of our 3 friends that we had before. So maybe we had a V, a U, and a W, but it's a generic node. What do I do after I got my signal? After I got my signal, I do Bayes rule. So here I wrote expectation instead of probability, but it doesn't really matter so much. So at time 0, I have a random variable. That's my estimate of S, given everything that I've seen. I've seen only one number, so I can say, oh, given this number, I believe that the state is plus with this probability and the state is minus in this probability. Everybody does that, right? So we had, everybody actually, all of the 3 nodes published to their friends what is their estimate of the state being plus versus minus, or in general, what's the expectation of this random variable. Okay, so far there's no interaction. Each of us got some information about the state of the world that we want to know something about. And, we computed what do we think by Bayes rule, what do we think the state of the world is given the signal that we got. Here is where the interesting part comes. At the next round, I'm going to incorporate the numbers or the estimates that I've seen by my friends, right? So remember our graph before was like this graph. So maybe this node observed this one and this one. So sorry, this was our U, this is our V. Let me erase it so it's more interesting. So now I over-erased. So let's make this U and this V. So now this node V is going to do the following. This node V is going to say, well, I have more information. So what do I have? My information at time t is the information that I had time t minus 1, plus everything that I observe. XWT minus 1 is everything that I observe. So, there was the original information that I got, but, I also talked to some people. Maybe this is bidirectional, but I also observe some channels. Maybe I observe the news or social media. And according to this, I'm going to update my information. Still, I do everything exactly mathematically. There's no heuristic. I apply Bayes rule, and Bayes rule tells me, this is my new estimate conditional probability or the expectation of the state given the world, given all the information there. And then this continues and continues and continues. Okay, and so since I'm going to talk about this, and again, I'm not going to prove anything. I just want to understand that to make sure everybody understands the model. And any questions about the model? So we do it iteratively. And everybody knows that this is assumption that I'm going to make. Everybody knows the structure of the networks. Otherwise, the Bayesian computation is a little more difficult because you also have to have a prior on the structure of the network. So we're going to make the assumption that they know the structure. Okay, so that's model number 1. Again, this model goes back to economics to, maybe not in this way, but definitely in this way, it was introduced in the 1980s. And now Will I have time to do an example? Maybe I will have time to do an example after we do the linguistic models. So the linguistic model is going to do exactly the same. So this is the same, this is the same, this is the same. Here's the first difference. So the first difference is now I keep track not on the expectation of S given the history. So everybody gets the signals at the beginning, it's all the same. The difference is now I have a distribution, I keep the full posterior. So FV naught is the posterior of the state of the world, what I want to know, given the information that I had. And the second difference is now I don't give you the mean of this distribution, I actually sample from this distribution. Okay, so this is something that I sort of learned from my colleagues who are doing computational linguistics, that you don't actually communicate maybe the mean of the distribution. What you communicate is you're communicating a sample from the posterior of that distribution. Okay, so I don't actually know the history, which is the first paper. So I'd be happy if somebody in the audience tell me. I found one early paper, but I don't know if that's the only paper. So that's what I do in the first step. And then in the next step, it's the same categorical composition, but it's a categorical composition where the basic operations are different, right? So what's my history at time t now? My history at time t now is the history that I had at the time t before, plus what I've seen from my neighbors. But what I know is my neighbors sampled from the posterior. They didn't tell me the means of their posterior. Then I have a new posterior. My new posterior is, the conditional distribution of what I'm interested in, given all the information that I've seen. And, and then I sampled something from my posterior and I broadcast it to all my neighbors that see. Okay, so the first reference, the first time I've seen this kind of model, but again, I don't actually know that's the first reference. This paper by Saborn and Griffiths, where they did Markov chain on people, right? So they said, there's a presentation in our mind, I think in images, and in order to learn something about this representation, I will let one person see a blurry image or pixels. Then I'll ask somebody else to draw it, and then there will be this resampling procedure from this posterior. So it's kind of similar to this model. This is a more general model, and again, many variants of this model were studied in the linguistic literature. And again, I'm happy to hear either now or later if there are other relevant or appropriate references. Any questions or comments? Okay, so these are the two kinds of models, right? So let me maybe comment a little bit. I don't have a lot of time, but let me try to comment a little bit about why. And I think here there's some more interesting theoretical open, philosophical open question. Why is the econ model different than the linguistic model? So in one of them, we are broadcasting the mean of the distribution. In the other one, we sample from the distribution. And the question is, why is the difference? So sort of at a high level, my view of this is that in econ, what happens is that in econ, you're always maximizing utility, right? And when you're maximizing utility, you are going to end up with maximizing some function, maybe some L2 error, you're going to get some expectation or conditional expectation. I think in linguistic, there's also, I don't know exactly what's the modeling perspective, but, there's also a value in the richness of what you say, right? Or, if you speak the language of physics, which sounds like some of the people speak, right? It's not that the energy, it's also the entropy, right? So you also want to include entropy in the model. And including entropy in the model is what causes you to say that you sample from the posterior distribution instead of optimizing some function out of the posterior distribution, right? So there's these two different models. Mathematically, like I said, if you use this categorical composition, they look very, very similar, except this actual operation that you're doing. Are you broadcasting the mean of the distribution or are you sampling from the distribution, right? So these are the two families of models that are studied. Again, mathematically, I think they're very, very interesting. And in the next 10 minutes, I'll just tell you a little bit of, what are the main questions. And interestingly, if there are differences or they're the same. Okay. Okay, so again, I was optimistic that I can do a simple example, but maybe I can do a simple example. So maybe I'll just do the simple example of the Gaussian model. I mean, with two players, right? So this is So here the model, I'll just tell you what the model is, just to be concrete a little bit. So the model is that the signal is drawn from the signal, there are two players and they both talk to each other, right? It's me and my friend talking to each other. And the model is, so you see me and I see you, so there's nothing sophisticated in terms on the graph. And the model is that there's mu that's uniform between minus infinity to infinity. So this is called an improper prior. And the signals that people get, S1 and S2, are drawn from normal distribution, the simplest distribution that we know, maybe with mean mu and variance 1. Okay, so what would happen here? So what would happen here are my two players. At time 0, so I'll do first the econ model. At time 0, this player will get S1 and will declare S1. This player will get S2 and declare S2. At time 1, both players watch each other. So I saw S1 and S2. I know how to do statistics. I know that my best estimate is S1 plus S2 over 2. You know that your best estimate is S1 plus S2 over 2. Game is over, right? Because we both found the posterior. We are now just going to, it's now we're just like being on the left or in the right of the US political spectrum. Right? We're just going to repeat to ourselves the same thing over and over again. So that's the econ model. What's the linguistic model? So at time 0, we still have this S1 and S2. But in fact, now there's a posterior, and I think the posterior, I didn't check it carefully, but I think the posterior is actually normal S1 with variance 1, and normal S2 with variance 1. Okay, now what I'm going to tell you, I'm not going to tell you the mode of the distribution. I'm not going to tell you S1 and S2. I'm going to sample, this player is going to sample A1 from this posterior. I want to be more interesting than just telling you the mode. And this player is going to sample A2 from the mode of this distribution. Now, what will happen here is, I know that I got S1, but now I want to incorporate A2. And if you think about A2, I think that the variance of the actual distribution of A2 is also normal with mean mu and variance 2. So what you will do as a good statistician is you will take a linear combination of S1 and A2, but I think it's going to be 2/3 S1. Again, I didn't check all of this calculation carefully, so I think it's going to be 2/3 S1 plus 1/3 A2. And you're going to do 2/3 S2 plus 1/3 A1. So that's going to be our new estimate of the mean. And therefore, our posterior is going to be normal with this and some variance which I didn't compute. And then we are both going to sample from this and continue getting linear combinations like this, right? So it's a more complicated model, right? Because we have entropy, because we are not just saying, what the mean is, there's going to be a more interesting discussion. And again, the question is what happens in post-discussion. Okay, so let me tell you what the questions are. I have 5 more minutes. So the main questions in this area, as presented in econ, but I think they're also interested in this linguistic, computational linguistic model, is agreement. Do the agents agree eventually? So we talk and talk and talk and talk and talk. Do we eventually agree? And learning, if they agree or if they don't agree, what did they get? So the goal of learning. I mean, we were interested in this S. So we had all of discussion. So maybe we agree, maybe we disagree, but did we learn something about S or no? So these are the 2 main questions, I think, mathematical questions in this model. Do people agree? I think that's, in collective intelligence, that sounds like a very relevant question. And the other question, collective intelligence is, what's the quality of what we learn? Okay, so I'll tell you very briefly what we know. And the answer is that, both of these things are in these models that I described work out well. So agreement, so in the econ model, in strongly connected networks, so strongly connected means there's a directed path from everybody to everybody. Okay, so I'll show you one. This is an example of a strongly directed network. But the original example that I had, this example is not strongly connected because nobody sees this guy. Right? So in a strongly connected network, agents agree, and they all converge to the same posterior, which we call X infinity. So we talk and talk and talk and talk. In general, it's not going to be 2 steps. It's not going to be even a finite number of steps. It's going to be many, many, many steps. We are going to talk, but eventually we are going to converge to the same posterior. And there are some work in economics, including ours. I'm actually not sure that I don't think I'm not sure what's the first reference there. We are not the first reference. We did it in a higher generality than other people. This is with Mueller, Frank, Sly, and Tammuz. But the posterior is actually the optimal posterior. What do I mean by that? What does it mean that x infinity is this? X infinity is the expected value of S given all the original signals. So this means that what we converge to eventually is the same as if there was one person who got all the information at the beginning and just computed. So even though there's a lot of overhead in this communication, and in general, it takes infinitely many rounds to converge, and you may be worried that information is lost in this process, it's not lost in the process. Eventually, everybody converges to this posterior, and the posterior is the exact posterior given all the initial data. Okay, so that's good answers from Econ. And the work that I wanted the work that motivated me to give this talk is this work with Yash Deshpanda that we haven't published yet or haven't even posted yet, is that the same answers are true in the linguistic model. So in the linguistic model, again, in strongly connected networks, sorry about the missing S, all agents agree and converge to the same posterior distribution, which I call F infinity. And there's learning in the sense that F infinity, this posterior distribution that we all converge to, is just the actual conditional distribution of S given all of the data that people got at the beginning, right? So in this model, again, people receive data only at the beginning. They receive data at the beginning, that's their individual intelligence, and everything from that point on is discussion of the collective intelligence. Okay, so let me maybe mention briefly, maybe mention in one slide, what is the difference between the model. So we saw at least one example where the speed of convergence is different, right? In this example with this, so the example that we had with the Gaussian model and the two players that look at one another, in the Econ model, they converged after one step. In the linguistic model, it actually takes infinitely many steps until they converge. The rate of convergence is exponential. But one of the things that maybe we want to understand better, I mean, we have some partial answers in this paper with Yash, is the difference in speed of convergence, and again we do it in the Gaussian case. Okay, so I'll stop here, and I'm happy to take questions. Thank you.